All right, for the online students, the students have just been working on these pulse sequence diagrams and creating their own and labeling everything. So now I'm just going to review each of these pulse sequence diagrams. We're going to start with our conventional spin echo. So here I would just add in conventional. So you can see it as SE, you might see it as CSE, so don't get confused by just the acronym. Conventional spin echo or spin echo, sometimes it's labeled as. All right, and I'm just looking straight off your papers, and I'll make corrections if there is any corrections, but it looks like everybody did an outstanding job on these. All right, so first pulse here, how many degrees?
90.
And this is an excitation pulse. Okay. I'm going to go ahead on this first line, also draw in another 90. So that I can later on create the TR that I need. So now, let's draw in our TR. 90 to 90, right? TR is always 90 to 90 except for which pulse sequence? Which one doesn't start with a 90?
Inversion.
Inversion. Inversion's 180 inversion to 180 inversion. Right? So getting more specific, above the horizontal line, what polarity are we dealing with?
Positive.
Good. And then obviously below it, we got negative. These right here, this rectangle and this rectangle might not be on the registry, but this is the most accurate way that you can draw these, because anytime the slice left gradient is turned on, you have to have a dephasing component to it and a rephasing component to it, just so that your spins stay coherent. The only gradient, there's actually no dephasing part of it, is our phase encoding gradient. That's why you don't see an extra rectangle here. But if you don't see these boxes, that's fine. The main ones are the ones above the horizontal line that you need to be considering. Okay? Here we have, once again, positive and negative. I like how somebody put right here, so down below, let me decrease my, here is our shallow phase encoding steps. And then up top here, we have our steep phase encoding steps. So that's why the hexagon is a little bit more accurate representation. Okay, what's another name for our frequency encoding gradient? Good. Right in the middle, you can divide this readout gradient. It goes along with peak echo. Let me redraw that. So then on the left of your readout gradient, it's usually called rephase. And then on the right, dephase. So your echo's rephasing to peak echo and then dephase. So here we can write peak echo. Okay, so here it has a TE, but we need to draw in the line associated with the TE. So TE's from what to what? TE's from what to what? 90 to what?
90.
That's TR. 90 to 90 is TR. 90 to what? 90 to the peak. So right as we turn off that excitation pulse to the peak. Good. All right. So I'm just going to put on here line 1, just because this is how they're going to ask you on the registry. This is line 2. This is line 3. Line 4. Line 5. And then I'm going to give you a sequence because obviously your RF pulses are being turned on, but when they talk about the sequence of events, they're really only talking about the gradients. So this comes first, the slice select gradient. Phase encoding comes second. And then our frequency encoding comes third. All right. So somebody did a great job of adding in the tau. So tau is from what to what? What do we think? Half TE. So good. So 90 to the 180 is the first tau. And then the second one is from 180 to the peak echo. So nobody ever really draws these in actual true representation, but this should actually equal this. You see that? Because it's this 180 should be timed to be right in the middle. Because you allow the signal to decay, you do the 180, and then it takes the same amount of time for it to regrow. So these two, just to let you guys know, even though they're not drawn to scale here, these should be equal in length. So then I'm going to put tau or 1/2 TE. And then I could do the same thing for right here. Tau. 1/2 TE. Everybody got that? All right. Let's see if I can scroll down and some of these things still go on to my dual spin echo. Okay. Some of these things still work, so I'm just going to erase some of them. So I don't need to label the lines again or which ones come on and off. So here we have once again our 90 excitation, and then we have 2 180-degree refocusing. So make sure you write on here refocusing, because you don't want to get the other 180 confused with it where it's inverted. We're refocusing the signal or the echo. All right. Let's see what else you guys added. Still have your positive and negatives. I'm not going to redraw those. We have our steep versus our shallow. All right, here we have two readouts now. So this is not our readout gradient. Anytime you have a readout gradient, it has to be over top of an echo. Because remember, we're sampling the signal. So this is readout 1. This is readout gradient 2. Notice how we only have one phase encoding step, or one phase encoding box here. And then that we don't have another one in between the 180s because we're really choosing one phase encoding step and we're creating two different image contrasts. So we're creating two images. That will come into play later on when you notice your fast spin echo where you're creating just one image and then you change your phase encoding step each 180 degree in refocusing pulse. Okay. All right, so E is this a long or a short TE? Okay, so this is TE1. We can say this is short for our proton density weighted images. Proton density weighted images have been replaced by what? Good, so I'm just going to put that off to the side. PD. So some of you have seen a lot of MSK. I know Melody's seen it. They still use proton density a good amount with your MSK imaging. Usually it's fat-satted too. So it's not a sequence we've done away with completely. We just don't use it for the brain anymore. All right, F here, this line. This is going to be our second TE. This is going to be our long associated with T2 weighted images. Okay. So if we draw an arrow, it's your T2 weighted image. Because we have a long TR and a long TE. That gives us a T2 weighted image where fluid is bright. We have a long TR and a short TE that gives us a proton density weighted image where our fluid is gray and we have a grayscale image. So then this one is associated with proton density. I like how somebody added in on this one. This is your free induction decay. And it's sometimes labeled as T2 star decay. Because it's decaying very rapidly. Remember, it decays as fast as 10 milliseconds. That's why we need to refocus it, because usually we don't image that quickly. 10 milliseconds. That's how fast it happens. Once you have the 180 degree refocusing pulse, then it's considered, so after 180 degree refocusing pulse, then it equals just normal T2 decay. Because some of our signals regrown. But your free induction decay is usually T2 star until you have that 180 degree refocus. So just off to the side here, proton density equals long TR, short T. Weighted equals long TR, long All right. Any questions with dual spin echo? Remember, you're getting 2 images for the price of 1 because there's all this time in between the 90 and 90. So why not go ahead and throw another 180 degree in there and get 2 image contrasts for utilizing this pulse sequence to the best of its ability. As a review, what are our 2 main categories of pulse sequences? We've only really talked about one so far, spin echo, but what's the other one? Which we're covering next semester. Gradient echo. Remember, the first slide of that PowerPoint presentation, you divide the pulse sequences into 2 main categories. You have your spin echo and your gradient echo. Remember that for your test. All right. So let's cruise on down to fast spin echo. So I'm going to have to erase everything here. So these right here, these 580 degree refocusing pulses, what are they also considered? Good. ETL. And we have 5 of them. So that's going to increase or decrease our scan time by 5. So we're going to fill 5 line decay space each TR period. So I'm going to put off this side. Decreases scan time times 5. So you remember the scan time equation. When you have an echo train length, you divide the entire thing by the echo train. So a lot faster. 90. And then the rest of these are 180s. Our slice select gradient, phase encoding, readout, and signal. So see how your readout is always over your echo. And then here, we're selecting a different phase encoding step each time. So here it creates the largest echo, so that's going to be our effective TE. So let me draw that in. So from your 90 to the largest echo, that's going to be your effective TE. So anytime you're dealing with fast spin echo or turbo spin echo, you always have to think effective TE instead of TE because you have multiple of them. I'm just going to put up here. Turbo. Or fast. All right, and when you get the largest echo, that means we are choosing a shallow phase encoding step. Our shallowest phase encoding step create the largest echo. So I'm going to write that over here. So shallow phase encoding step. Put it right on top here, that first one. The smaller echoes are created by selecting a steep phase encoding step. Okay, and then everything in between will be associated with a little bit less steep, a little bit less shallow. But remember, the one that creates the largest echo is your effective TE. So if you select a shallow phase encoding step way down here, your echo should be larger, and your effective TE will be longer. Okay? So that's how you choose and get your desired image contrast for a fast spin echo. So I'm going to put over here the large echo will go to the middle of K-space, which is always associated with our signal to noise or our contrast to noise. So the large echo goes to the middle of K-space. The smaller echo will go to the edges of K-space. Go to edges of K-space. And that will be our resolution. So that's why you see a little bit of blurring on our higher echo train length images, because we have smaller and smaller echoes going to our outer edges of the K-space, our resolution. So that's kind of one of those downfalls to a longer echo train length. What did I not draw in? Then it restarts all over again. So your next 90. So then from 90 to 90. Here's your TR. Okay? Any questions on that? Last one. Inversion recovery. The only other one here is a gradient echo, but remember, you don't need to know this for this test. We'll cover that next semester. So inversion recovery. So these have been labeled already with the degree, but we need to be a little bit more specific. So it says 180, but let's put under there, inversion. Because we start with an inversion pulse. Excitation, and then refocusing. Oh, okay, they actually have it there. You can see it. They do have it right here, inversion pulse. Slice select gradient turns on anytime an RF pulse gets turned on. Get your phase encoding gradient. Your inversion time. Your echo time is from still your 90 to your peak echo. This is still your readout gradient. You only have one readout gradient. You could add in your rephase and dephase and split it in half, your peak echo. The only thing we're really missing here is your TR. So I'm going to draw a larger rectangle because we're going from 180 to 180. So then your TR is from here all the way to the next 180. Okay. So your inversion times, you have two different inversion times for a stir versus a flare. So your TI is short for a stir. That's why it's called short tau inversion recovery. Just write it out. Short tau. And then your TI long or flare. Can somebody give me the numbers? Stern of the TI times for stern flare.
There's 150 to 175.
Okay, hold on one sec. Give me 1 second. Fluid attenuating IR. Okay, so what was it again, Nick? I'm sorry.
Stern, it's 150 to 175.
For what Tesla strength?
1 T.
1 T? Does it say 1 T?
It's Tesla.
I think it's for 1.5. 1.5 Tesla. And then, okay, so what's our ranges for flare?
1700 to 2200.
Remember, these are milliseconds for 1.5 Tesla. Okay? So this time right here is going to be extended for your flare, because remember, water takes longer to recover versus fat. So your TI is going to be a lot shorter before everything starts. Let's see if you guys added anything else on here. All these look great. Any questions? All right, let's take a break. I'll make some copies of these and hand them out, okay? How many do we have here? We have almost everybody. 8 people? Mr. Jasmine and Rachel. I'll make them copies.